Okay. Yeah, I think that goes to small classes. I like to have everybody here. Although we're still down 3 people, but
Yeah, where's this one?
I already knew about the rest. That we're not going to come here. So, okay. Continuing with the, in my opinion, the boring part of the course, the linear algebra review, and hopefully review is at least useful to some extent, because I'll just dive boredom up here. Okay, so where I left off last time, the essential operation of matrix vector multiplication y is equal to ax. A is m by n. X is an n vector, and y is an m vector. So each component of the output vector y is a sum. Although another way to look at this, a perspective that'll become useful later on when we deal with matrix multiplication, you can think of this as a dot product of the ith row of A and with x, because we think of the ith row of A as a row vector with n elements. We're multiplying corresponding components of these two vectors and adding them all up. Okay. Now, one quick example of this I want to do. It's a very important way to, useful way to understand matrix vector multiplication. If I have then my vector x is so that if I go ahead and compute A times x, what's really happening is matrix vector multiplication amounts to taking a linear combination of the columns of A, where the coefficients in the linear combination are determined by x. So if you were to carry this out according to a formula, that would amount to, so 10 times the first column, so it's the first element of x times the first column, plus second element of x times the second column. Whoops, totally messed that up. First column, not row. Row. Can't believe you guys missed that.
I think I totally chuckled over here.
Oh, my hearing sucks. Okay.
I got it.
Okay. Plus the third element of x times the third column. Okay. And you can see that kind of from the formula because each element of x is multiplied only by entries of the corresponding column of A. So if we took all these together for all different values of I, you can see where this comes from. Okay. So for instance, if you're multiplying a matrix by the vector 1, 1, 1, 1, 1, all ones, basically what you're doing is you're just adding up all the columns. Okay. Now, one very important use of matrix vector multiplication is system of linear equations of this form, a11 x1 plus so forth, a1 n xn is equal to b1, and then we keep going. I wrote a system like this out before on Tuesday. A m n x n is equal to b m. What's happening here is this is matrix vector multiplication. Okay, so that's quite convenient that we now have a succinct way to describe these systems. Okay. So now that we have a multiplication operation going here, we'd like to be able to expound on that for the purpose of being able to solve systems of linear equations. So if we step down to the trivial case where m and n are both equal to 1, because we certainly know what to do in that case. Okay. So ax equals b reduces to just a scalar linear equation. So ax and b are all numbers now. So therefore the solution is just equal to a to the minus 1 times b, so a multiplicative inverse, provided that a is non-zero. So where, of course, because it's multiplicative inverse, a inverse times a, or a times a inverse, is 1, which of course we know as the identity element. So I'm going over these exceedingly elementary concepts because we want to do the same thing for matrices, for a case where m and n are greater than 1. Okay, so we need some sort of we need some sort of appropriate multiplication operation that would have an identity and an inverse to be able to solve more general linear systems. Now, how we can arrive at such a multiplication operation is by going back to the perspective of linear transformations, because if we recall, f is a linear transformation that has a matrix A in given bases. And to make things simple, we'll work with the standard basis of whatever vector space we have for both the domain and the range. So that would mean that f of x is equal to a times x. So we have f with domain Rn and range Rm. All right. Now, I'm going to include a second linear transformation, G, that goes from Rp is this domain into Rn. And it is a linear transformation whose matrix in the standard bases for these spaces is given by B. Okay. So, so if I have x being a vector in a domain of G, And then let y be a vector in the range of f. And the way I'll define y is f of g of x. So it would be the matrix A times the vector b times x. I have the matrices of the individual linear transformations, but if I take the composition of linear transformations, that again is a linear transformation that can be shown directly, which I won't bother doing here. But what we'd like to know is, what is the matrix C of the composition of these linear transformations, F composed with G? So we want to apply both linear transformations in one shot. So F composed with G has its domain Rp and range Rm. So it bypasses Rn. That's the output of G and the input of F. Okay. So C, therefore, is a M by P matrix, whatever it is. But we want to be able to figure that out. And we can do that using matrix vector multiplication. Okay, so each component of the output vector y, that's a, b, x. So using the formula for matrix vector multiplication applied to A, that would be a sum for j equals 1 to n of ai, actually I'm going to use the index k for this, k times the kth component of the vector I'm multiplying by, but that vector is b times x. So now I have to use the matrix vector multiplication formula again on bx, kth components. So we have aik, and now what we have here is the sum for j equals 1 to p of b k j x j. All right. So now what I'd like to do is I want to express this as a single matrix vector multiplication. So that would be Cij xj, where C has to be determined. So if I go ahead and match these formulas up, right? So what I would do is I could take this inner summation, pull it out, the outside, and see, okay, what is it exactly that's multiplying xj? Because this is my Cij, and what I get is k equals 1 to n, aik b kj. So what we have here is C is the matrix product of A and B, where the entries of a product are defined by this formula right here. And A is M by N, B is N by P. As you know, those dimensions have to be the same for this operation to even make sense. AIK, BKJ. All right. Now, those of you who have ever taken a 685 class with me know that this comes up actually being able to recognize a matrix product in reverse to be able to understand an operation as a matrix product. So this formula is very good to have in your mental cache. Okay. So any questions about how that was derived? I know it's a familiar formula, but I just find it fun to show where it comes from. Okay. Alrighty. Now, this operation doesn't even make sense to go both ways unless the two matrices are square and the same size. But even if you can do that, so M, N, and P are all equal, so you could compute AB and BA, but in general, matrix multiplication is not commutative, unlike ordinary multiplication. However, but it is associative, meaning AB, even when it is defined, is not necessarily equal to BA. However, A times the product BC is equal to the product of A and B all multiplied by C. So you have those things. Okay. All right. Now I'm going to go through a hodgepodge of operations that are introduced into the linear algebra class that we're going to need all the time. But first I want to mention that last time I talked about vector spaces. Now, instead of all M by N matrices, all matrices of the same size, over a field F, and again, that could be either, for our purposes, the real numbers or the complex numbers, forms a vector space. And that vector space has dimension M times N, the total number of entries you have in the matrix. So it's almost like you can think of it as being isomorphic to the vector space Rmn or Cmn. It's just that where if you take these matrices and you reshape them into a big long vector, or you can leave it as a matrix. So, so then you have your operations for matrix addition, which is far more straightforward than multiplication. Than just adding entries component-wise and obey all the usual laws of addition. And you also have the scalar multiplication. So multiplying a matrix by a scalar, you're just scaling all of the entries of the matrix by that scalar alpha. Okay. Certain properties, and these come directly from corresponding properties for these operations on a vector space. You have a distribution property. Well, these really tie into relating addition with matrix multiplication. Okay, so you can do that. And you also have you don't have commutativity of matrix multiplication, but with scalar multiplication you do. So if I have alpha times AB, you can move a scalar alpha around in whatever way you want. You can associate the alpha with the B, or you can associate the alpha with the A. And where the alpha goes within the product, the result is the same. So scalars you can move around however you want. You just can't change the order of the matrices involved. Okay. Now, very important operation for us is the transpose. Now, matrix B is defined to be the transpose of A. So A is m by n, and B is n by m. So the dimensions are reversed. So Bij is equal to Ji. So you're reversing the sense of rows and columns. Now, A is n by n, square matrix. We say it's symmetric if A is equal to its own transpose. Also, we say it is skew symmetric also known as anti-symmetric if A is equal to minus its own transpose. Well, I have a friend who's Dutch, and she will always say skew symmetric. So I'd have to stop from laughing. Okay. Now, some properties of transpose. So first of all, you take the transpose of the transpose that brings you back to the original matrix, because you switch rows and columns and then you switch it back. Transpose distributes over addition, so the transpose of the sum is the sum of the transposes. And then for products, very important, transpose of a product is the product of the transposes except in reverse order. That's obviously can be verified using the definitions of all of these operations, if you're really bored. Okay. Now, I should mention, speaking of symmetric and skew symmetric, every matrix can be written as a sum of a symmetric matrix and a skew symmetric matrix. If I write A this way as 1/2 A plus A transpose, and then I have plus 1/2 A minus A transpose. So if you were to simplify this, of course, so the A transposes would cancel, but 1/2 A's would add together and you'd get A again. But this matrix is always symmetric, and you could verify this using all the properties I just wrote over there. Or property 2, really, or properties 1 and 2 together. So this matrix is called the symmetric part. And this is the skew symmetric part. It's kind of like how any function can be written as a sum of odd and even functions. Like if you have f of x plus f of minus x over 2, that's the even part, and then f of x minus f of minus x over 2 is the odd part. Similar to like how you write a complex number in terms of just real imaginary parts, like z plus z conjugate over 2 is a real part, and then z minus z conjugate over 2i is the imaginary part, stuff like that. Okay, there'll be very similar decompositions. Okay. So one thing that's interesting about a skew symmetric matrix is the entries along a diagonal are always equal to 0 because you have aii. Take the ii entry of both sides, you get minus aii. So those entries have to be 0. Okay. Now, for the most part, we will be dealing with real numbers, real vectors, real matrices. But this may come up now and then. If A is a complex matrix, a lot of things that operate or results or techniques that involve a transpose for real matrices, if you want to generalize to a complex case, generally you would not simply use transpose again. The way you would generalize to a complex case is use what is called the Hermitian transpose. And that uses a superscript h instead of t. H for Hermitian. So the Hermitian transpose is you take the regular transpose, but then you also take the complex conjugate, which is what the bar is for. So including a conjugation is what allows things that are done with the transpose for real matrices to carry over to the complex case. So that's something to be careful about. So then, so the generalization of symmetric to complex matrices is that A is equal to its own Hermitian transpose. And we say that A is a Hermitian matrix. And different books use different notation for this. Sometimes instead of an H, they might use like a star, because then they're talking about the adjoint of the operator, thinking of matrix as an operator, and star is often used for that. Or sometimes like a little dagger or a cross is used to indicate adjoint, but that could be confused with other notation. Okay, but for the most part, in the numerical linear algebra world, we use the H. Okay. Right. Just a little more time to see how much further we can get. All right. Now, a couple of very important operations that are built off of transpose that we'll be using all the time. In fact, I don't even remember learning about these in an undergraduate linear algebra course. I feel like I should have been taught that level, but okay. Let's get this too. I mentioned dot product before, so the way we could express dot product, also known as an inner product, using the notation that we've seen so far, like using matrix multiplication and transposes, is x transpose y, because y is n by 1, it's a column vector, x is also n by 1, but you're transposing it, so that would be 1 by n. So the product is 1 by 1. It's just a number. So if you work out what it was using formulas for matrix multiplication, you would get a familiar dot product. Well, that probably came across in calculus. Okay, so this is a way that can be expressed in the linear algebra world, just x transpose y. So we'll be seeing that all the time. And this is where it's very important to keep in mind that by convention, we assume vectors to be column vectors. If you want a row vector, you take the transpose. Okay. And another very important concept that x and y in Rn are orthogonal, which is same thing saying a perpendicular in n-dimensional space. If their inner product is 0. So in orthogonality we'll be dealing with all the time. Okay. Now, here I assume that x and y are real vectors. If they were complex vectors, we'd say x Hermitian transpose y is 0 for orthogonality in complex vectors. You don't have a valid inner product if you just use regular transpose with a complex vector. Because you might have a situation of a vector having like a negative magnitude. Okay. Now, no doubt you've heard the term dot product before, because that's a term that's used in calculus. But it seems strange to call it an inner product unless we also have an outer product. And we do. An outer product, speaking of this, putting a shoe on your foot, instead of x transpose y, we have x, y transpose. So here we assume that x is in Rm, y is in Rn. So for an inner product, both vectors x and y have to have the same length, the same dimension, but that's not true for the it's not necessary for the outer product. Now, x is m by 1, and then y transpose would be 1 by n. So the dimension of the entire thing is m by n. So whereas the inner product is just a number, an outer product of two vectors is a matrix. So the way we would define, and this can be worked out using the matrix multiplication formula, is each entry is no longer a sum, like in a general case. It's just a product. So I have like x1, y1, x2, y1. And so the whole first column is just x times y1. The second column is x again, but times y2. And so on, to the last column, which is x times yn. So, in other words, every single column is a multiple of x. You can also say that every row is a multiple of y transpose. So, all the columns are parallel, all the rows are parallel. So you could say there's actually only one linearly independent column. There's also only one linearly independent row. And this is going to become relevant for like the very first homework problem that you'll have to do. Okay, so some examples. So for convenience, I'll make both these vectors of dimension 3. So x is 1, 0, 2. Y is 4 minus 1, 3. Okay. So now what I'm going to do is take both the inner product and outer product of these vectors. So inner product, x transpose y, so that would just be multiplying corresponding components and adding them up. So we get 4 plus 0 plus 6, so we get 10. And inner product is commutative, so if I did y transpose x, I would also get 10. Then for the outer product, so x, y transpose. So I'm going to have, actually I'm just going to write the entries of x and y over and over again, x for columns and y for rows. So x I'm going to have 1, 0, 2, 1, 0, 2, 1, 0, 2. And then I'm going to write the elements of y. So I'm going to have, or y transpose rather, so I'm going to have 4 minus 1, 3, 4 minus 1, 3, 4 minus 1, 3. And so what I'm going to get is just by multiplying all these together. So 4 minus 1, 3, 0, 0, 0, and then 8 minus 2, and 6. So as you can see, each column is a multiple of x, each row is a multiple of y. Okay. Any questions about these operations? All right. Now, one interesting use of the outer product, suppose you have a matrix and you want to make a change to just one entry. So an outer product is a good way to express that in a formulaic way. To illustrate that.
With the outer product?
Outer product, yeah. So to add a certain amount, call it C, to Aij. Okay, that's what and then I'll use B to refer to the updated matrix. So the idea is B is obtained by just taking A, but in one entry, a particular ij entry, you're going to add C to it. So we can say B is equal to A plus EI, EJ transpose. Should have written a C first. Hold on. Well, that doesn't really matter, but okay. So I can just do that. Because this matrix, EI, EJ transpose, is going to be entirely the zero matrix, except for the ij entry, which is going to be 1. So, as an example, I have A plus 5, E2, E1 transpose. Whereas E notation I described last time, EI is a vector where all components are 0, but the ith component is equal to 1. Okay. So if A is a matrix, say 1 minus 3, 7, 2, 5 minus 8, 4 minus 6 minus 9, and if I look at E2, E1 transpose, well, E2 is 0, 1, 0, so three-dimensional space, and E1 transpose is 1, 0, 0. So those are the two vectors that you're taking the outer product of. So when you carry out that multiplication, so every column is a multiple of this. Every row is a multiple of this. So you're going to get 0, 0, 0. But you're going to get 1, 0, 0, and then 0, 0, 0. So this is the only entry, the 2, 1 entry, that gets touched. So B turns out to be just A, except this entry has 5 added to it. Now, I haven't, well, when you add on an outer product of vectors like this, as a name, it's called a rank 1 update. I've not yet talked about rank. Probably was discussed in your first linear algebra course, and it's something I will cover at some point. It's called an update because you're updating some entry of a matrix. And so one of the first homework problems is to prove that any outer product of vectors, anything in a form like UV transpose, only has rank 1. All right. Okay, I want to put an intermediate step here so you can see where that comes from. Because it's 0, 1, 0 times 1, 0, 1, 0 times 0, and 0, 1, 0 times 0 again. And that's why it turns out to be all zeros, except for this one entry right there. But they're using the same thing I did in the previous example, just for vectors that are mostly 0.
Can you just throw your notes away?
What?
Can you just throw your notes away?
If I don't have any mistakes to make note of, yes. Oh, I seem to have. Okay, my page got a little out of order, but.
All of this would have helped with the coding from the summer.
Oh, from what?
The coding from the
Talking
summer.
about 684
Yeah.
or 68, not his box, 684.
Yeah. Oh well. Okay. Let's see. What do I have next? Don't really feel like doing that one. Oh, okay. Okay. Oh, I think I actually won't be behind. Well, not yet anyway. Okay. Now, to give some helpful perspectives on matrix multiplication, there are certain ways of representing a matrix in terms of its rows and columns that are helpful. Okay. So let's suppose that A is n by n. So I can write A in this way in terms of its rows as a collection of row vectors stacked on top of each other. And A has m rows, so there would be m such vectors. And each one of these is a vector in Rn. So these are the rows, or at least once we transpose them. They're row vectors. So this is called a row partition of A. But another way to write A, which actually probably is somewhat more useful for us, is in terms of its columns. C1, C2, Cn. So this is called a column partition of A, and each of these vectors, Cj, is a vector in Rm, assuming that the matrix is real. Okay. So, for example, if A is a matrix 1, 2, 3, 4, so we have, write as a row partition, R1 transpose and R2 transpose. We can also write as a column partition, C1 and C2. So we can fill in the vectors R1 to R2, C1, C2 from the entries of A. So R1 would be 1, 2, R2 would be 3, 4, C1 would be 1, 3, C2 would be 2, 4. All right. Okay. Now, from everything that I've just been showing you, I can give you 3 different ways to look at matrix multiplication, and each of these perspectives is going to be helpful from time to time. Basically, these first few lectures are just a preview of a zillion things. So this class is quite a tease that way. Actually, I had someone complain about that. Okay. So so one perspective, which I kind of brought up with regard to matrix vector multiplication, but certainly valid for matrix multiplication too. If C is a matrix product of A and B, then you can say that Cij is equal to the inner product of the ith row of A and the jth column of B. So each individual entry you can think of as a dot product or inner product. What?
Yeah, R2, yeah.
Yeah.
It's, the second row vector, in your example.
Yeah, what about?
It's supposed to be transpose. No, over here. A equals.
Yeah, and then the R transpose.
Oh.
Second, yeah. There you go.
Yeah, okay.
Don't you get bonus points for finding mistakes? Or is that just in in the notes?
Oh, in the notes.
No. On his website, do you read all the links, Stephanie? I look at the cat link every semester. But they don't change.
Yeah,
So
yeah.
It says if you get
Well,
bonus
that-
points if you find errors in his.
Oh, yeah. No one's done that in quite a while. So,
It doesn't count in lectures.
what?
Does it not count in a lecture?
Well, I haven't really thought about that, but.
Wish I get points for you. That's all.
I appreciate it.
Okay.
You're
Well.
being
She's
kind of
fine.
stubborn right now, but I'm
Yeah.
trying.
Well, at least someone's reading for the whole site. So. Okay. Number 2. All right. And so again, if C is equal to AB, and if I do column partitions of C and B, I don't need one for A for this. So C C has these columns, C1, C2, CP. So A is n by n, B is n by p, so the product is m by p. And if I also have a column partition of B, so C and B both have p columns, then these columns of C and B have a simple relationship that Cj is equal to A times Bj. So in other words, every column of the product is a linear combination of columns of A. And the coefficients of linear combination are determined by the corresponding column of B. Okay. Let's see. I guess you could say you could also make a similar connection between the rows of C and the rows of A, where you're taking like a row of A, like Ri transpose times B. Okay. But normally this relationship is more useful to us. And finally, another perspective in terms of outer products, where, okay, so C is equal to AB again. Probably I should have written that once. Up top, A has this column partition, A1, A2, AN. And then B has a row partition. So B has to have n rows, so B1 transpose, B2 transpose, all the way down to Bn transpose. Then what I can do is I can express C in terms of outer products. So C turns out to be A1 B1 transpose plus A2 B2 transpose all the way to AN BN transpose. So we can express C as a sum of outer products. So in general, AJ, BJ transpose. Okay. And that's something that's going to be surprisingly useful to us, even though I can't imagine this is brought up in any particular undergrad linear algebra course either. But we are a bit past that level now. So for a lot of matrix decompositions that we'll see, and it's often very helpful to express those in terms of outer products. All right, questions about these? All right. Well, I have until 6:25, don't I? Okay, I have 12 minutes left. Okay. See how much further I can get. I mentioned subspaces last time, so to return to that, okay, and some very important terminology you're going to need. Okay, so we'll assume that A is n by n. So the range of A, and that's sometimes it's written as range of A, also abbreviated ran of A. So that is equal to, instead of all vectors in Rm, where m is the number of rows of A, that can be obtained by multiplying A by some vector in Rn. So it's all possible outputs of the linear transformation described by A. All right. Now, A times X is a linear combination of columns of A. So you can think of it as the span of a columns of A. So another name for it, arranged, is the column space of A. So arranged and a column space refer to the same thing. All right. Now, the dimension of it, and it turns out because it's a span, it's a subspace. The range is a subspace. So the dimension of a range of A, that is called the column rank of A. Now, you can also describe a row space of A. So the span of all the rows of A is and that is a subset of Rn, whereas a range is a subset of Rm. So a dimension of the of a row space of A is called the row rank of A. Now, who remembers how the row rank and column rank relate to one another? Well, good thing we're doing this review then. All right. The row rank is always equal to the column rank. So we don't really bother with just distinguishing them. So we just call that the rank of A. So just one number captures it all. So the number of linearly independent rows of a matrix is always equal to the number of linearly independent columns. Okay. Now, we can also say that the rank, therefore, has to be less than or equal to the minimum of m and n, because your columns are in Rm. You cannot have more than m linearly independent columns. You cannot have more than n linearly independent rows. So whichever is smaller than 2 dimensions, that is an upper bound on the rank. So a couple other terms that come out of this is if a rank of A is equal to the minimum of m and n, we say that A has full rank. In other words, it has the maximum possible rank, given its size. If the rank is strictly less than that maximum value, then we say that A is rank deficient. And so rank deficient matrices are kind of a pain to deal with. Okay. Now, so a very important subspace of Rn that is related to the range is called the null space. Okay. So the null space of A, which is abbreviated as null of A, so that's equal to the set of all vectors x in Rn, such that if you multiply by A, you get the zero vector. So certainly the zero vector itself is in a null space, but there may possibly be other vectors too. Okay. There we go. Oh, we got out early. Lucky dogs. Okay. Okay, I guess I could do the same thing, but all right, I'll finish this paragraph and then I'll stop because we're doing pretty well schedule-wise. Now, the dimension of the null space is called the nullity of A. And there's one very important theorem, I believe it's called the dimension theorem, that states that if A is n by n, then the rank of A plus the nullity of A is equal to n, the number of columns. So that's true in general. Okay. So range and null space are going to be important subspaces that we'll deal with at various times. So. Okay. Well, aren't we moving right along? Okay. So I think we'll call it good for, yeah, so I'll certainly be able to finish up the linear algebra review portion of this on Tuesday. Not bad for starting 10 minutes late. But I'm done.